Hello everyone, I hope you're doing well. In this video, we'll be solving this problem which is related to free particle in quantum mechanics. So let's see the problem statement and we'll dive directly into the solution. The statement says that consider following functions coskx, sinkx and e to the power iota kx. So these are three different functions that we have in here. Then prove that coskx, sinkx and e to the power iota kx are eigenfunctions of free particle Hamiltonian with v equals 0. This information is it's sometimes given and sometimes you have to remember it that a free particle is actually a particle that experiences zero potential. So that is something that you should know as well. It's sometimes given in the statement and it's not in other cases. So what we have to do basically here is to prove that these three functions are eigenfunctions of free particle Hamiltonian. Alright, so it's a kind of eigenvalue problem and it's also related to free particle systems in quantum mechanics. So let's see how we can check that whether a given function, these three functions, whether they are the eigenfunctions of Hamiltonian operator or not for a free particle. Let psi1 equals cos kx. I'm letting here all of the wave functions so that we have some representation for them, and psi3 equals e to the power iota kx. Alright, and we know that Hamiltonian for free particle is given by, let's say we'll write the Hamiltonian in general, is given by Hamiltonian operator, that is in 1D, which is minus h squared by 2m partial square by partial x square plus v. For free particle, we have v equals 0, so we can get the Hamiltonian for free particle specifically. So this is the free particle Hamiltonian. Alright, and this is the Hamiltonian that we are gonna use later on. Alright, now this is the Hamiltonian and these are the three functions that we need to test whether they are the eigenfunctions of this Hamiltonian or not. For that purpose, we have to use the eigenvalue equation. If you already know, then you can write it down and see whether your equation matches with mine or not. So we know that the eigenvalue equation for Hamiltonian is given by when a operator applies on psi, any psi, it equals to e times psi. When this equation holds where e is any constant quantity, it should be a constant quantity. When applying Hamiltonian on psi, it's when we will apply Hamiltonian on psi on any wave function. If the wave function comes back multiplied by some constant quantity, if this situation holds, then psi will be the eigenfunction of Hamiltonian. If the wave function doesn't come back, alright, multiplied by some constant quantity, if that situation doesn't hold, then the psi will not be the eigenfunction for Hamiltonian. Alright, I hope you have got this situation. So a given wave function will be an eigenfunction for the Hamiltonian if when Hamiltonian applies on that function, the function comes back with multiplied by some constant quantity. Okay, that is how we confirm whether a function is the eigenfunction for Hamiltonian or not, and the constant quantity that we get is called as the eigenvalue. Alright, so let's test it first and you'll understand what I'm saying. So we'll test first for psi1. Okay, we'll test whether it's the eigenfunction or not. We'll put the value here, psi1 equals, we'll put it here on the left hand side only because that is something we know. This is Hamiltonian for free particle, then it will be applied on psi1 and psi1 is actually cos kx. Let's solve it. We have minus h squared by 2m and its double derivative, which means partial by partial x dot partial by partial x on cos kx. And let's find out the derivative of cos kx. This one will be solved. cos kx, its derivative is minus sin kx. Alright, dot derivative of its angle is kx. And here when we will be finding out the derivative of kx, k is a constant. It will come outside here, and partial x by partial x is 1. So we are left with this situation that it's minus sin kx, and it's minus h square k by 2m partial by partial x minus sin kx. This minus and this minus cancel out, and we are left with plus. Minus minus is plus. So let us find out the other derivative now. It's h square k by 2m partial by partial x on sin kx. Now we are supposed to find out the derivative of sin kx, which is actually cos kx dot derivative of its angle. Every time when you are finding out the derivatives for trigonometric functions, you change that trigonometric function from one form to another, like sine changes into cosine, and it is always multiplied by the angle's derivative. Okay, we always find out the derivative of its angle. And again, this is cos kx, and k is constant, so it will come here, and we are left with partial x by partial x, which is 1. h square, this is k square by 2m cos kx. And we had this situation in the left hand side, and this is in the right hand side, and we can see this is psi 1 actually. Cos kx is psi 1, k square by 2m, and it's psi 1. Alright, and we can see that this is a constant quantity. It doesn't contain any x variable in it. What makes a quantity not constant is when it's having some variable. It doesn't contain any variable. It doesn't contain x. It doesn't contain t. Okay, so we can see that they are all constants. H cut is constant, k is constant, 2 is constant, m is constant. So it's constant times psi 1, and here this is actually energy eigenvalue then. So since the psi 1 satisfies the eigenvalue equation with E1, the energy corresponding to this psi 1 will be called as E1. So it's h square k square by 2m. Hence, psi 1 is eigenfunction for free particle Hamiltonian. Alright, and we'll be doing it the same way for the other two wave functions as well. We'll see whether they satisfy the eigenvalue equation or not, and if they satisfy, then we will say that they are the eigenfunctions for the Hamiltonian operator of free particle. And now we are gonna check for psi 2. Okay, and we'll apply the Hamiltonian operator on psi 2. Hamiltonian operator for free particle is minus h square partial square by partial x square, and psi 2 is actually sin kx. We can see that it's sin kx. Now let's do it for this. It's partial square by partial x square. It means there are two derivatives. We'll apply them one by one. Minus h square by 2m partial by partial x. Sin kx changes into cos kx dot derivative of its angle. Now we know that what we are getting. So minus h square by 2m. This k will come outside, and partial x by partial x is 1. So we are left with partial by partial x cos kx. Now let's find out the other derivative, and it's cos kx changes into minus sin kx dot derivative of its angle, which will be k will come outside, and it will become k square, and it's x, and it's 1. Okay, minus minus plus, so it's h square k square by 2m times sin kx. Alright, and it was this thing on the left hand side, we can see, and sin kx is actually psi 2. And we can see that on applying Hamiltonian operator on psi 2, we got h square k square by 2m times the wave function back. And that was what I told you people, that when this thing happens, when a constant times the wave function comes back, the same wave function, not a different one, the same wave function comes back, then we say that this wave function is the eigenfunction of the operator that we applied. So here the same statement will go, since this sign is to show the since operation or statement in mathematics. Since psi 2 satisfies the eigenvalue equation with E2 equals h square k square by 2m, exactly the same energy as we got for the first case. Hence, psi 2 is the eigenfunction for free particle Hamiltonian. Now let's do it for the last wave function or function, which is check psi 3, which is e to the power iota k x. Let's apply Hamiltonian or psi 3 and see what happens. And we have this free particle wave function, or the operator, then wave function is this. Now let's apply it. We'll solve multiple other problems where we'll be having that eigenvalue problems, where we'll see that when the function is not the eigenfunction for the operator, and we'll have a variety of problems as well. So stay tuned for practicing all of those problems, because they are really important in terms of exams, because teachers really want to know that whether you understand the eigenvalue equation or not, and the requirements that we pose into the wave functions. Now let's apply the derivative on exponential. So the derivative of exponential works like that the exponential comes as it is, no change on it, derivative of its power, which is iota kx. We can see iota k is constant, so it will come outside, and we are left with partial x by partial x. It's x that's left. Partial x by partial x is 1. So minus h square iota k by 2m partial by partial x on e to the power iota kx. Let's find out its derivative again, which will be same. I wrote iota first, okay? Pardon me. It's iota kx again, okay, as it is, derivative of its power minus iota h square k. Now iota will come outside, so this iota and iota becomes iota square. This k and k becomes k square e to the power iota kx by 2m, and it's partial by partial x of x, which is 1. We know that iota square is equals to minus 1, so it's minus into minus 1 h square k square by 2m e to the power iota kx, minus minus plus, so it's h square k square by 2m e to the power iota kx. When Hamiltonian applied on psi 3, this is actually psi 3, we got h square k square by 2m times psi 3. Let me clarify here that it's the exceptional case that we are getting the same constant term, okay, when we are applying the Hamiltonian. It's not important or necessary condition, it could be different, but the only thing that is important is that whether we are getting a constant quantity times the wave function back or not, okay, that is what is important. It's not important that we are getting the same eigenvalue again and again. No, that is not a requirement. That's the exceptional case that is happening in this free particle wave function, because the energy values are actually definite and they are not changing. So that is what we have got, h square k square by 2m times the psi 3 back. Hence we can write that since psi3 satisfies the eigenvalue equation with this E3 eigenvalue, hence psi3 is the eigenfunction for free particle Hamiltonian. Alright, so in that way, we have checked whether a wave function is the eigenfunction for a given operator like Hamiltonian operator or not, and we have understood that how we can apply and get a useful information from eigenvalue equation. Okay, so that is it for this video, and we'll be doing multiple other problems. Stay tuned and do check out the playlist Quantum Mechanics Beginning, where I'm uploading all of the relevant content, while the other playlist, which is about quantum mechanics, it contains the many different topics, which is when we are into midway or at the end of the quantum mechanics journey. So they're all helpful and you can check out, and if you can't find any, let me know, I'll do that for you.